Our next speaker is Doug Head. And Doug Head is the Director of Mission Critical Systems for the ASCO Power Technologies company. And Doug has joined us as a first-timer today, so please give him a warm welcome. And as you see him in the hallways today, please shake his hand and introduce yourselves. So ladies and gentlemen, I'll bring him up right away. Mr. Doug Head.
Got the clicker? Okay. Good morning. Sort of. I guess we're running a little late. So, if I were to ask you, picture a data center, what does that look like to you? I think most of us, myself included, would picture these huge server farms, rows and rows of racks that can support massive amounts of compute. And that's right. Those are out there. You're thinking Microsoft, you're thinking Google, you're thinking Facebook, you're thinking Amazon, but that's not the only construct of data center that's out in the market today. So whether you're a generator dealer or a generator owner, like a company owner that wants to sell 3 megawatt generators, you can do that. You can sell those things in mass quantity. But if your company finds that their sweet spot is between 400 kW, 800 kW, those data centers are out there too. We can all participate in the data center market. You just have to understand it. You have to understand the needs of the data center owner. You have to understand the construct. How do I sell into this? So to that end, today, what I'd like you to take away is some new strategy, some new idea of how to get involved. How to get involved in the data center space, this massive growth due to big data. We're all wearing Fitbits. We're all pushing pictures of our kids into the cloud. So it's all out there to be had. We can all be a part of it. So whether you're involved today or not involved today, I'd like you to take away a new idea or a new strategy that gets you into that market. So let's talk about data center evolution. We started in the 70s with these huge monolithic stacks, and those were supporting mainframes. And those guys were worried about reliability. They're going to go and they're going to buy one generator, and it's got to be the most reliable generator on the planet because they got one. They're going to go and they're going to buy one transfer switch because, and it's got to be the most reliable one out there because they're only buying one. And if either of those things go down, they're going dark, and they didn't want that. These guys we could influence. These guys we could sell value. They wanted service and support. They wanted to hear that. Then we moved on to the next generation of data center, the client-server data center. And they went from thinking reliability to availability. Now, I know we use those words interchangeably a lot, but they're different. Reliability is really more of a function of the product that you're applying to the data center. Availability is focused on uptime. How do I keep my data center up all the time, right? And they don't have to have the most reliable equipment on the planet, although reliability is a function of availability, because they're buying more than one. They're building redundancy into the infrastructure. And then we're moving into, or have moved into, what I would term as the cloud generation today. And these guys look for scalability. They look for speed. They look for efficiency. It's a completely different mindset. Those guys look at compute as a resource, and they want us to look at KW in the same way. So we're going to start with the enterprise data center. What is an enterprise data center? So when you think enterprise, think financial, think healthcare, think retail. A data center that's built to support core business functions. And there's usually 3 components to that data center. There's the internal. So those are applications that are supporting human resources, they're supporting payroll, they're supporting manufacturing. There's the external, and those are applications supporting business-to-business transactions. And then there's the internet, and those are applications supporting business-to-consumer transactions. And their focus is availability. They want to be up all the time. And then we move on to the colo data center, the co-location data center, the multi-tenant data center. These guys are real estate agents. And they come in a couple of different forms. You've got the wholesale co-location data center, and all they're doing is they're providing power and cooling to white space. And their client comes in, they put their racks down, they put their servers in, they don't need any managed services from that data center. And then you can look at the retail data center, the retail co-location data center, and those guys, they're selling managed services in addition to power and cooling. They've got a rack sitting there for them. They can come in, they can drop their servers in, and the data center will take care of everything else. And then you can look at the hybrid. Now, the hybrid is, let's say, up to a megawatt client, and they're coming in, they're dropping a rack down or 2 racks down, and they use some managed services. And these guys, you know, their focus really is, I'm going to say varies by type, because build to suit sort of skews what their primary focus is. I might have a Microsoft that goes to a digital that says, look, build me a 30 megawatt data center, and Microsoft might have a very specific idea of what they want. But generally speaking, when a colo is building for themselves, they are focused on first cost. They have to be competitive to their clients. So if they're buying the most expensive stuff out there, they can't be competitive. They can't write competitive agreements. And what does the colo landscape look like? Well, here's where things start to really get interesting, right? If you look, these are just 15 cities across the globe, right? How much power is available in a city, and how much has been developed in that city? And that's what's great about being in the colo market, is that, let's take New York, for example, right? That's pushing 800 megawatts of available rental power. But look on the left chart, the dark bar is the developed portion, the yellow bar is the undeveloped portion. So, and if you look, that yellow bar is roughly twice the size of that dark bar. So what that means is if New York has already developed 800 megawatts and it's available to rent, they've got another 800 megawatts that's allocated to build out. So across just those 15 cities, you've got roughly 6,200 megawatts available for rent that's been developed, and they're ready to develop another 6,200 megawatts. The real estate is just sitting there. Those guys are budgeting for that. It's not going to happen tomorrow, but that's what they're looking for, is that type of growth, 100% growth in those existing facilities. And it's not on here, but if you were to drive through Ashburn, Virginia, who's been to Ashburn? Raise your hand, right? There's got to be a 10-mile radius of 1,000 generators sitting there of all different sizes with all different applications. Now let's move on to the cloud. What's a cloud data center? Well, a cloud data center is really just a data center built to support cloud services. These are guys that build the data center, they build out the white space, they're putting in the racks, they're putting in the servers, and they're running their client's application in the cloud so they can access it anywhere. And these guys are focused on speed. I need to deploy fast. And when you're thinking of the cloud, again, everybody, their first thought is Google and Microsoft, and that's right, because those guys are in a race to own the cloud. Google, Microsoft, Facebook, they're all going up against Amazon, who owns the majority of the cloud. But there's other cloud deployments. Most co-locations have a cloud platform now. So even if you can't be involved in, say, like a Google or an Amazon, you can look at those colos to be involved in the cloud deployment. And we bulk colo and cloud together a lot just because colo typically has a cloud platform. So this was a study done over 145 45 companies spanning 750 cities. And this accounts for 60% of cloud services and 80% of colo. And if you read through there and nothing catches your eye other than $18 billion spent on data center infrastructure in 2016. I was being a little optimistic. That was me just dreaming. 18 trillion would be fantastic. Right? But this is a market we want to be involved in. And this is a market we can all be involved in. And then, what's a hyperscale data center? When we tend to think hyperscale, we think customer, not data center type. So hyperscale means Google, Microsoft, Amazon, Facebook, right? I know I keep bringing up the same ones. I do love those. I'm not going to lie. But the hyperscale data center is actually a data center that's built with an architected design to allow massive scale of compute. They want to scale up fast and they want to scale up really big. And those guys, again, are focused on speed to deploy. Now, they typically have a couple of different teams in a hyperscale data center. In the deployment of that, they've got strategic teams that set standards in equipment, standards in design, and then they have operational teams. And when you think hyperscale, think big. Now, we always have to be careful, right? I can't throw up numbers that I've signed NDAs for, but if you just go and search hyperscale, this is what you can find. It's all right there available. Microsoft, Apple, Google, 3 million, almost 3 million square feet of IT already deployed. And this is just in the US, right? And just those sites, they're way bigger than that. Here's what an early generation data center looked like. And we love these things. Medium voltage generators, medium voltage switchgear, paralleling switchgear, super complex. There's only a few of us that could do it. This is a $60 million sale for somebody. And they focused on availability. You could sell service, support, right? You could sell the value of your product. And they listened, and they knew what a generator was. And they knew what switchgear was. And this shift, this evolution of the data center wasn't just an evolution in application. It wasn't just an evolution in power architecture. It was an evolution in thought. Because, you go to a data center owner today, they may not know who you are. They may not really know what the generator is for. Now, they're going to know what it's for if it doesn't start. But they just simply may not know. And that was the hardest lesson for me to learn. And I'll tell you, I remember the day that I was taught that lesson, and that was an ugly day. And I'll tell you the story, and Don Blackman and Armin are sitting in the crowd, and if I have a job at the end of the day, it might be a little surprising, but I'm going to tell you the story anyway. I got a phone call that said, hey, Doug, we need you this week. We need you to fly in. We need you to talk to this guy, and let's talk about data centers. And this was years ago. I wish it was more years ago, but it was maybe 6 or 7 years ago. I wish it was longer. That would imply that I'm a little smarter than I was, but I was dumb. So I jumped on a plane. I walked into a conference room, and it was a pretty intimate setting. There's 4 or 5 other what was Emerson guys sitting there, and there's the CTO of Lockheed. And he said, hey, I want to build a 30-megawatt data center in a bunker for missile defense. I won't tell you what country, but it was a really cool plan. And I got up, and I had this 65-inch touchscreen, and you could write on it, and it was the coolest thing ever. And I thought, this guy is going to love me when I get done. So I talked to him for an hour about switchgear and how great ASCO was and all our power transfer solutions. And I was ready to go. I was ready to write the deal right there. And I got done at the end of that hour, and I might as well have been talking to him about building a peanut butter and jelly sandwich for as much good as it did me. Because not only did he not understand what I was talking about, he didn't care. We speak a totally different language. And I walked away from that meeting thinking, holy cow, I have to completely change my strategy. This is not going to work. And I know Armin's going to ask me later, did you get this job? This is not a success story. No, I did not get that job. That was a bad meeting for me. So if they're not focused on us, and if they don't know who we are, what are they focused on? One of the major contributors to energy costs is inefficiency. They will burn up energy in inefficiency that will waste them thousands, if not millions, in a year. And I know everybody has heard PUE, power usage effectiveness. And really, it's just a measure of the efficiency of a data center. I would measure the total facility demand versus the demand consumed by the IT. And I get a number, right? Anywhere from 1.2, some people claim 1.08, that's crazy. 1.2 to 8 sometimes. Some of them are terrible. And so what you have to understand is how you load your UPS in those data centers will either lose you a bunch of money or really help you become a lot more efficient. So if we take this chart on the left, for example, And I apologize if there are guys in the room that sell transformerless UPSs. This is not representative of everyone that's out there. I know some of them claim to be more efficient than this, have a better curve than this. But if I take a transformer-based UPS and I load it up to, let's say, 40% utilization, right? That's the word they like to use, utilization. And I'm running 91% efficiency, and I want to output 400 kW through that UPS. At 91% efficiency, I'm putting approximately 440 kW into it. So I'm burning, just throwing away 40 kW. And at 8 cents a kilowatt hour, that equates to about $10,000 a year. And if I'm a little data center and I buy a couple of these, $10,000, $20,000, that can make a big difference. Whether I expand or don't expand, whether I hire new talent or don't hire new talent. Now, if I'm a big data center and I'm deploying 100 of these, that's a big number. I'll let you guys do the math. I'm not even going to try to do it in my head. But take that 10,000 multiplied by 100. That's a huge number. And you have to understand that. That's the way they're thinking. They're not thinking generator. They're not thinking switchgear. They're thinking efficiency. And then the chart on the right was an analysis done by Emerson a few years ago. It referred to as Energy Logic 2.0. And what that said was, well, wait a second, let's look at the total savings from top to bottom. Let's not just look at the UPS. Let's start at the server, because every time I transform in a data center, I have an efficiency loss. So let's start at the server, let's go up through conversion, let's go up through the PDU, let's go up through the UPS, let's go up through the building transformer. What do I end up with? I could save 1 watt at the server, and that could equate to almost 3 watts at the building input. So just thinking efficiency saves massive amounts of money, and that's where their head is. So when they go to design their power architecture, what questions do they ask themselves, and what questions should we be asking them? 1, market segment. What am I serving? What's my application? And that leads me to all the other questions. What's the budget? What's availability? How do I want to scale? And keep in mind that when they ask a question or they give you the information of how do they want to scale, guy comes in and says, I want to scale at a megawatt. That doesn't mean he wants a megawatt generator. How many people knew that? Raise your hand. Nobody, come on, somebody knew that. You're just being lazy. That's cool. So if I want to scale at a megawatt, what does that translate to for a generator every time they push a meg of IT in? 2 megawatts, right? Because I have to add cooling. Even at a 1.5 PUE, now I've got 1,500 kW, and I haven't even talked about battery charging, and I haven't talked about any supporting infrastructure. We're talking about a 2 megawatt generator every time they want to scale a megawatt. And then how quickly? How quickly do they want to deploy? So to kind of understand their thought process and understand how they design, you have to understand uptime tier classifications. So the Uptime Institute created these classifications to provide a measure of availability of a data center design. And as you go from 1 to 2, 2 to 3, 3 to 4, availability goes up, but cost also goes up. So tier 1 is just basic capacity. I need in, I build in. Tier 2 is redundant components. I need in, I build in plus 1 on the component level. Right, but tier 1 and tier 2 both note that it's only 1 active delivery path. Tier 3, I need in, I build in plus 1 system to support 2 delivery paths, 1 active, 1 passive. And then tier 4, I need in, I build 2 in, and I have 2 active paths. So let's take a look at examples of what those tier classifications look like. Tier 1, I need in, I build in. That's what this looks like. Super efficient. I have 1 power path all the way down the chain from the generator to the IT rack, and I can load that UPS up to its rated kW value and make it as efficient as possible. Also, not fault tolerant at all. Single points of failure scattered all through the system because you have 1 power path and no redundant components. Tier 2, I start putting in redundant components. I need 1 generator, I buy 2. I need 1 UPS module, I buy 2. Or if I needed 3, I would buy 4. So can be very efficient, depending on how you design your UPSs. But still, just a single power path. Anything happens in that power path, we're going dark. The only thing we can overcome is some component failures. So then I go into tier 3. Now tier 3 gets a little more interesting because I have to develop 2 power paths. Right? So what you're looking at is a pretty typical tier 3 design. So now we've moved from what the enterprise data center would use, tier 1, tier 2. They're usually pretty comfortable with engine paralleling. They're relatively comfortable with fault intolerance. But tier 3 is where you start to see co-location, cloud, and hyperscale. And we're going to spend some time on this, and the reason I want to spend time on this is the fastest growing market segment of the data center landscape. Hyperscale, colo, cloud, right? So we're looking at a dedicated reserve or a catcher system. I'm sure many of you have already heard those terms. And let's talk about how this works. So under normal conditions, I have a reserve system that sits there unloaded. I accept that loss, right? That efficiency loss, I just have to accept. I have 100% of block A going through that power path, going through block A. I have 100% of the IT demand of block B going through the power path dedicated to block B. The reserve sitting unloaded. I can be very efficient, and this is massively scalable. So I can make this very, very small, or I can make it really, really big. Now, when I go into planned maintenance, because I have to be concurrently maintainable, that reserve system picks up whatever system I took down to put into maintenance, or if I happen to have a failure. Now, the problem with the reserve is you've got one bus that goes to everything. And if that reserve becomes overloaded, anything connected to it is going down. But you can be very efficient, and you can also scale huge. Super, super simple. Right? So when you hear ratios, we were looking at a ratio initially of 3 to feed 2. I have 3 blocks, but really only 2 loads. This is a ratio of 9 to feed 8, or 9 to 8. I have 9 blocks. One of them is a reserve. I only have 8 loads. I've seen this go as big as 27 to 25. And really, the biggest limitation is the footprint. How far can I really run that reserve bus before I start running into voltage issues? Now, another common type is the distributed reserve or the distributed redundant system. 3 to 2 distributed redundant system is very common. This is deployed in a lot of places. But it's a lot more complex. All those systems are interlaced so that if I take any system down, the 2 remaining active systems pick up that critical load. So under normal conditions, I have 33% of the entire IT load going through each block. When I go into a planned maintenance, I have 50% of the building load going through the 2 remaining blocks. Now the problem with this is you have to balance the system. There's not a lot of companies that are really good at distributed reserve systems. They tend to stick to small ratios. There's one company in particular, it's probably the biggest distributed reserve system I've seen, it's a 9 to 8. Normally you'll see this rolled out in a 3 to 2 or a 4 to 3. And that's kind of as big as it gets. And the other problem with distributed reserve systems, in a 3 to 2 ratio, they're not terribly efficient. You're buying a lot of UPS, you're buying a lot of batteries, you're not using much of it. So let's go through this one more time, but let's look at the numbers. So if I have a 3 to 2 distributed reserve system, and my entire IT load is 1,500 kW, that means I have 500 kW at each block. Each one gets a third. Now, because I have 500 running through and I have to distribute out any kind of a planned maintenance or failure to the remaining blocks, I have to upsize those UPSs. I can't size them at 500 kW. I have to go up to 750 kW. Because when I have a planned maintenance, what was sitting at 66% utilization, 500 kW out of 750 kW is now sitting at 100% because I split that planned maintenance load between the 2 remaining systems. So now I'm running at 100% utilization, as efficient as I possibly can be, but my normal condition is only at 66%. And you also have to keep in mind, whenever you recommend any kind of a ratio system like this that you're building to scale, as you increase ratio, relative MTBF goes down. So if I start with 2n plus 1 as my approaching 1, everything goes down from there. And you can kind of see the scale to which it goes down. Now, tier 4, 2n data center. I need n, I buy 2n. 2 times everything, 2 active delivery paths. Under normal conditions, I have 50% of the entire IT load going through each block. Now, when I have a planned maintenance or a failure, I have 100% going through the remaining active block. Super, super easy to deploy. It's just 2 times everything. But it's also expensive, and it's not very efficient. Because the best utilization you can get out of those UPSs is 50. And that's only if you're willing to go 100% under planned maintenance. So what you would normally see is probably 40% on those UPSs. Now, a lot of times, this is very traditional 2n enterprise deployment. And the thing that changed here is that we added tiebreakers between the 2 blocks. You have to be careful when you recommend a system like this. So what you're looking at is scripted sequences of every possible combination with 2 transitions of that block. There's almost 100 sequences when I add those 2 tiebreakers in. So I went from a couple of transfer switches, throwing back and forth, picking up that IT load, to 100 different program sequences when I want to do opened or closed transition. So just be careful, be aware that sometimes when adding tiebreakers, it's not as simple as you might think. There's a lot going on there. Common mistakes in architecture design. I see these all the time, unfortunately, right? Whenever somebody says, I want tier 3, I want tier 4, don't give them a paralleled system. They only have one paralleled system. You can't put everything onto a common bus because that becomes a massive single point of failure. And if you have a bus failure, you've lost your primary source of power. In a tier 3 or tier 4, you have to view the generator as your primary source of power. The utility is only a cost-saving convenience. Whenever you connect independent bus segments with one interrupting device, you have to be concurrently maintainable. So what that means is I go to maintain one bus, it's hot up to that interrupting device, and I can't actually maintain that interrupting device. You have to have 2. And the other mistake that I see, I probably shouldn't say mistake, but that's what it is. The other mistake I see a lot is a data center owner will go to somebody that maybe doesn't have as much experience, and they'll say, look, I want to deploy 400 kW of IT. Oh, well, let me give you 8 generators in the swing configuration. That guy's going to love you because he's going to spend a couple $100,000 on his UPS and $2 million on a switchgear. So be careful recommending an over-designed system. Make sure whatever system you recommend or whatever system you design for your owner meets his criteria and doesn't go so far over that it's maybe funny to you, but not so much to him. So let's go through a sample, right? I've got an owner, and I'm going to walk through the crowd now because you guys are quiet, and we're going to make people guess at how much stuff costs. I've got an owner that says, oh, people are leaving now. He's scared. This guy in the jacket right there, him specifically. Oh, yeah, turn around. That's you. I've got an owner that says, all right, I've got a mixed-use facility, office space, data center, and my day 2 IT load is 300 kW. And my office space is 500 kW. So what did we say before? When a data center owner says how he wants to scale, does that mean the size of the generator? No. I have to worry about cooling, and I have to worry about supporting infrastructure. And he also says, I want tier 3. So let's go with a typical tier 3. Let's look at a catcher. Can be very efficient, easy to build out, easy to operate. So who wants to tell me in this tier 3 how much those generators cost? I'm going to come around and stare at somebody in a really creepy way if I don't start getting some answers. Somebody's getting pointed at. Give me a number on the generators.
I'm a UPS guy.
Well, that's not going to help me. 100,000. Wow, that's great. I'm going to buy generators from you. That seems like a really good number for two 500s and what is that, a 300? $100,000. Somebody, I'm sorry? Anybody else got a guess? 2 million. Yeah, I'm not buying generators from you. This guy's working up a number. 210. I like that number. That sounds like a good number. He's giving me the right thing. Who wants to give me a number on the ATSs and the distribution? You look so scared. I won't ask you. 250. Yeah, we're definitely doing business. I'm going to sell you that stuff. We're good. Somebody give me a number on the UPSs. I know I just ran into a UPS guy. It was you. You're smiling. Give me a number on the UPSs.
75.
75. A piece?
Yeah.
Wow, that seems like a good number. It's not the number I thought. But let's look at the total cost. So this is what I said. I like the 210 number way better. 75 I like a lot, and somebody said 200, 300 grand for the ATSs. I like that because that's what I sell. So $850K for this system. Now, let's take a look at it this way. This is a hybrid 2-in. I'm going to do 2-in power, but I'm only going to do +1 cooling. So a couple of 800s. Give me a number on a couple of 800s. Anybody, throw a number out there. 350. That seems high, but we're going to go with that number. Who wants to give me a number on the ATSs? 125. That sounds good. I don't know if we're going to do business, but let's roll with that. UPS? I'm going the same guy because I didn't see another UPS guy in the room. How much for the UPSs? 300s. It's got to include batteries. 50 a piece? Holy cow, that's fantastic. I'm going to recommend everybody to you if those are real numbers. Yeah, I don't think so either, but yeah, that's cool. 700. So I saved, what, 130K? I gave them a higher availability system. Now, I lowered my efficiency a little bit because I went with a 2-in, but I don't have an unloaded system, right? So keep in mind that one platform does not fit everybody, right? I can't throw everybody into the same thing and make it work. Clearly, at this scale, my thing's falling off here. Clearly, at this scale, the dedicated reserve doesn't make sense, but the 2-in does. And so what's out there for us, right? The enterprise data center, we should all love these guys, right? We can sell to these guys. We know how to sell to these guys. They're like healthcare. They're like industrial. They understand generators. They understand our value. We can sell them power transfer equipment, paralleling switchgear, generators, and they're focused on availability. Colo and cloud. These are guys that are looking for fast. Their secondary focus is cost. They're looking for a good price. And we can sell them power transfer equipment and generators, really ATSs, or some ATS-like structure. And for me to go to them and prove that I can do the job, they're looking for standardization. They don't want to reinvent the wheel. They want to do the same thing over and over again. And then hyperscale, speed. Power transfer equipment, generators. And what are they looking for? Standardization, industrialization, right? Large volume pricing. This is a commodity sale for those guys. Now, some other things to be aware of that are happening within the data center, these are already happening, is they're playing with the position of the UPS. So they may look at a centralized UPS. They may look at distributed UPS throughout the rack or at the row. They may be looking to open compute. If you haven't seen open compute before, really all it's doing is it's extracting the power supplies from the servers and putting that within the rack, generally supported by lithium ion in the rack. It's a way to take the heat out, and it's a way to standardize equipment and drive costs down. But in all of these layouts, what's the one thing that's consistent? I know I made it the biggest block, but there's more consistent stuff in there. The ATS, the generator, they can't get rid of us. They still need us. From a power perspective, other than conditioning, that UPS is just a bridge to us. And not that guy, though, because he sells UPSs. There we go. Now, the other thing that we're seeing these guys do is we're seeing them move to the edge. They've already done it. They're moving out to the edge. They want to get closer to their customers. So if you look at the numbers going from core data centers to local and regional data centers to network closets and server rooms, look at the change in number, right? How many potential customers do I have when I'm just looking at the edge? Almost 3 million sites existing today. They need a little generator, they need a little transfer switch. We'll sell those all day long. And really what the edge is doing is it's moving them closer to the customer. So, I don't know about you guys, but in my house, we stream everything. Nothing is watched live. And when my son can't watch his cartoons and Netflix goes up to 76% and freezes for 2.5 seconds, you'd think the zombie apocalypse hit my house. I got a kid, I got a wife, all coming screaming at me. Regional or global infrastructure redundancy. Now, a few years ago, we all thought this is the end of the generator. They want to get rid of us. There's no more transfer switching equipment. There's no more generator. They're just going to build data centers everywhere, and they're going to make that network redundant in such a way that they can just accept a failure. And if you look, this is the Google Cloud. This is a great example of this type of infrastructure. But for them to get rid of the data center, you have to make one big assumption, is that they have enough capacity in that network to accept the failure. And really, with the traffic we see today, they don't. So for example, if I'm running 80% utilization across the globe in all my data centers, I can only accept a small failure before that 80% turns into 100%. Now I'm completely loaded up, so which ones do I allow to fail? But what this is doing, it's not eliminating the generator, but it is moving us to a lower availability design, and some companies are already doing this, some of them are looking at it. Why am I going to build tier 4 or tier 3 data centers when I could build tier 1 or tier 2? Because I can accept that availability. I have a big enough infrastructure that I can accept the failure. And I always think it's kind of interesting to go through the 451 research data predictions for the data center for 2017. I know we're totally off the rails on time, so Kim's shaking her head. I can't tell if she's telling me to shut up, just ignoring me. So we'll roll right by, and if anybody wants to talk about those, please come see me. None of them were earth-shattering. They were all sort of obvious ones, or they just totally missed the mark, like talking about microgrids. Any questions? I'm done. I'll get off the stage. I'll shut up.